Okay, so ready, Moumanti?
Yeah, I am.
Yeah.
Yes, thank
Okay,
you.
so we'll now start our second lecture. It's by Moumanti Podder. She's recently or somewhat recently joined ISA Pune. Before that, she has did a postdocs in various places, NYU Shanghai, Georgia, and Washington, and she did her PhD from NYU. So today she will talk about combinatorial games on multi-type Galton-Watson trees. Okay, go ahead, Moumanti.
Okay, thank you so much for that. So yes, there are a couple of terms in the title, combinatorial games, which I will come to explain. These are usually two-player games with perfect information, and also talk about what multi-type Galton-Watson trees are. And then I'll give an overview of some of the results that I have. This is from a pretty recent paper. So as many of my mentors would say, when you give a presentation, try to tell a story. So every story has a beginning, and this is how mine began. I was looking at a paper named Galton-Watson Games by one of my collaborators, Alexander Holroyd and James Martin. So they were studying, again, combinatorial games, but on rooted Galton-Watson trees, not multi-type Galton-Watson trees. So I don't know if this is something that I probably didn't need to explain, but I thought if this is a mixed audience, I should probably define what Galton-Watson trees are. So Galton-Watson branching process. So this is a stochastic process that was introduced by Francis Galton and Henry Watson around 1875, if I'm not too mistaken. And the whole idea was to try and model ancestral family lines of England. So the idea is as follows. You start with a single individual called the root, which I denote by phi, and then you let it have a random number of children. So let's say that x naught denotes its number of children. So x naught will follow a certain distribution. This is known as the offspring distribution. I call it chi. If let's say that x naught is, if the root has no child, then of course the process stops right there. If x naught is equal to some positive integer m, where m is not 0, then let's say you name the children of the root v1 through vm, and then each vi is allowed to have, again, a random number of children, which I denote by capital Xi, such that x1 through xm, these are independent and identically distributed random variables, each with distribution chi. Okay, so and then you continue this process. This process could come to an end after a finite number of, after a finite time, in which case you get a finite tree. Otherwise, you get an infinite tree. And notice that we're talking about rooted trees where we specifically identify the root phi. I call the resulting process script t, this weird notation. So if, and this is something that is classically known, that if the offspring distribution chi has expectations strictly greater than 1, then there is a positive probability that this tree is going to survive forever, meaning it's going to be an infinite rooted tree. Otherwise, with probability 1, it's going to be a finite rooted tree. So for the purpose of the games that I'm about to describe, this tree script t will be visualized as a directed graph in which, if you consider any edge uv, so when I write it like this, it means it's undirected. So between, let's say, two vertices u and b, where u is the parent and v is the child, then you direct the edge from u towards v, and you write it like this with parentheses to denote that this is a directed edge that goes from u to v. Okay, so here are the description of the games that Ander and Martin studied. So the idea is that you choose any vertex of script t as your initial vertex, and you place a token on that vertex, a marker or a token on that vertex. And then there are two players who will take turns to move the token along directed edges. Okay, so you start off at the root. Let's say the first player moves the token to a child of the root, then the second player moves the token to a child of that child, and so on, it continues. Okay, so there are three different kinds of games that Holroyd and Martin studied. These are, first of all, the normal game. So in the normal game, you simply call the players P1 and P2. So you mark them as first player and second player. and then you play the game, you let the players play the game. Just to make it very clear here, a couple of things that, so we are playing the game on a tree which has already been generated following the Galton-Watson branching process, meaning that you fix the environment. It is a realization of the Galton-Watson branching process, but it is fixed, and this tree is known completely to both the players. Okay, so they can use, you know, a look ahead strategy to figure out how they're going to play the game. Also, they are both playing optimally, meaning that let's say that P1 is destined to win the game. So as I said, this is going to be a perfect information game. But let's say that P1 is destined to win the game. So then P1 tries to win the game as soon as possible, whereas P2 tries to prolong the duration of the game as much as possible. Okay, so both players are trying their hardest to play the game to the best of their abilities. So in the normal game, whichever player fails to move the token first will lose. In the misére games, I don't know if I'm pronouncing this correctly, but let's say misére games, it's the opposite rule to decide the outcome of the game, meaning whichever player fails to move the token first wins the game. Okay, so when will you fail to move the token? If you reach a leaf vertex from where there is nowhere to go. Okay, so so these two are kind of like opposites of one another, and many of their analysis actually can be quite closely related. Then there is a third class of games known as escape games. So here you call the players stopper and escaper. These are like special names given to the players because of the roles they play in the game. So in this game, if either player fails to move the token, then stopper wins. Otherwise, escaper wins. Okay. So in these two games, it is possible that neither player ever encounters a leaf vertex in their path, and the game just continues forever, in which case you end up with a draw in the normal or misére games. But when it comes to escape games, there is no question of draw. So either the game continues up to a finite point of time, in which case stopper wins, or else the game continues forever, in which case escaper wins. Okay, so
there's a question in chat. Who plays first? I guess it applies to 3. Maybe BB has that question.
Yeah. So we will talk about that. So if you can let either player play the first round, and accordingly the analysis will change slightly. So for example, in these two games, the players are moving symmetrically, but in this particular game, it does matter whom you allow to play the first round. And in the setup that I'm going to talk about in my work, it definitely matters which player plays the first round. So we will talk about that. It will be like 2 separate analyses for the 2 cases.
Sorry, ask a question?
Yes.
So when you were explaining the games, you said that P1 tries to win and P2 tries to prolong the game? I mean,
no, if P1 is destined to win the game, then P1 tries to win as fast as possible, and P2 tries to drag the game as much as possible.
Okay.
Yeah, so like both are trying to play optimally.
Okay.
So now I talk about my setup, which is slightly more actually quite a bit more complicated. So in the paper, of course, I talk about a more general setup where the multi-type Galton-Watson trees can have many different classes of vertices. But here, for the sake of the talk, I'll talk about only bi-type Galton-Watson trees, meaning that every vertex B has a color or a label associated with it. It's either blue or red. Okay, and I call this label sigma sub V. And now when so everything else remains the same as I described before for the Galton-Watson branching process, except that now when a vertex V gives birth to a random number of offspring, the distribution of this random number will depend on the color of V. Okay, so given that the color of V is blue, the probability that V gives birth to M blue and N red many children is given by some chi sub B of M comma N. So this is a bivariate distribution now, and the subscript B here indicates that you are conditioning on the parent vertex having color blue. Similarly, conditioning on the parent vertex having color red, the probability that V has M blue and N red children is given by chi sub R of M comma N. Again, this R stands for the fact that the parent vertex has color red. Okay, so you say that a directed edge u to v is monochromatic if both the parent u and the child v has the same color, so both blue or both red, or else you say that the edge is non-monochromatic. Okay, so and here are the variations that I need to incorporate into my games for this particular setup. So in my version of the games, again, you have either players P1 and P2 for normal and misère games, or you have stopper and escaper for the escape game. And once again, you know, they have this token and they're taking turns to move this token along directed edges. However, their moves are no longer symmetric. So in case of the normal and misère games, P1, and in case of the escape game stopper, they're allowed to move the token only along monochromatic edges. And in case of the normal and misère games, P2, and in case of the escape game escaper, are allowed to move the token only along non-monochromatic edges. Okay, so now you are sort of restricting the edges along which the two players can move the token. So now what happens is if a player is unable to move the token, it's not necessarily true that the player has reached a leaf vertex. It could mean that let's say P1 is unable to move the token from a vertex U. That means that U does not have any child with the same color as U. Okay, so this could also be the case. So slightly more complicated games. So, but the outcomes are decided by the same rules as before. So normal game is won by whoever is lost by whoever fails to move the token. Misère game is won by whoever fails to move the token, and escape game, again, if either player is unable to move the token, then stopper wins, otherwise escaper wins. And once again, draw here is not possible. Okay, so this is the setup for my games. And now I come to a little bit of insight into how I analyze these games. So I will only talk about the normal game for the sake of this analysis, because for the misère and escape games, a lot of things are similar. And anyway, I don't have the time to like go into details. So for the normal game, so I will try to explain the notation now. So this capital N stands for normal. So I'm emphasizing the fact that I'm looking at subsets of vertices in case of the normal game. This here will either be a W or an L. And what will that stand for? It will stand for, W will stand for winning, L will stand for loss. I didn't define D here, but there will also be a set called ND, which stands for, you know, when the game ends in a draw. Okay, and the first subscript here indicates which player plays the first round of the game. Okay, and this the second subscript indicates what is the color of the initial vertex. Okay, the color of the vertex where the token was placed before the game began. Okay, so for example, NW1 comma B, this is the set of all blue vertices, because here you have a B, so that's blue vertices V, such that if V is your initial vertex and if P1, so see I have one here, so I'm talking about P1 playing the first round of the game, then P1 wins. Okay, that's again, it's indicated by this W here. Likewise, you define NW1R. So I also tried to color code these things. So this means set of all red vertices V, such that if V is your initial vertex and P1 plays the first round of the game, then P1 wins. Similarly, when you look at NL1B, this is a set of all blue vertices V, such that if V is your initial vertex and P1 plays the first round of the game, then P1 loses. Okay, and likewise you define NL1R, where it's set of all red vertices. Okay, so likewise you can define NW2B, NW2R, NL2B, and NL2R. So in all of these definitions, P2 plays the first round of the game, and the colors indicate what is the color of the initial vertex, and the W's and the L's indicate whether P2 wins or loses. Okay, so we also define some level n sets. So for any positive integer n, I define NW1B superscript n to be the set of all vertices that are, first of all, in NW1B, meaning that if the game starts from such a vertex and P1 plays the first round, then P1 wins. But also this N indicates that the game will last for less than N rounds. Okay, so so this is like extra information here that not only will P1 win, but she is guaranteed to win the game in less than N rounds. Okay, so the game will not last for more than that. By convention, I set NW1B0 to be the empty set. Likewise, you can define the level N subsets for all the other kinds of sets of vertices. Okay, so now this completes my definition of subsets of vertices when it comes to the normal game. Let me talk about probabilities now.
Can
Yes.
I ask a question?
Yeah.
So I'm confused as to what distinguishes NW1B and NW2B, for example. I mean, P1 starts initially and P2 starts initially. I mean,
Correct, but then their moves are not symmetric. One is allowed to move only along monochromatic edges. The other one is allowed to move only along non-monochromatic edges.
Okay.
That's why. Yeah, but this was the same, like you pointed out, these two were the same things for Martin and Holroyd, but not for me.
Okay.
Yeah.
Thanks.
Okay, so the probabilities are, so all I have done is I've changed the uppercase letters to the lowercase letters. That's all there is really. So small nW1B superscript n is the probability that the root belongs to capital NW1B superscript n, conditioned on the root being of color blue. Okay, so I use this conditional probability. It really doesn't matter at the end of the day because you would know what the probability of the root having color blue is. So I just focus on the conditional probabilities. So likewise, you define, all the other level n probabilities, and then you also define the probabilities without the level n thing. So NW1B, for example, is the probability that phi belongs to capital NW1B conditioned on its color being blue. Okay, so here's a lemma which I have, I've stated very briefly, but it actually requires you to go through some compactness arguments. What you can basically show is that capital NW1B superscript n, as n increases, this gives you an increasing sequence of subsets which ultimately converge in capital NW1B. What this means intuitively is that, other than, of course, the analytical aspect of it, what this means is that if a game is not destined to win in a draw, you will be able to determine in a finite number of rounds that it is not destined to end in a draw, and you will be able to determine who is supposed to win. Okay, so you can find some positive integer n such that if it can be a very large positive integer, but if you play the game long enough, you will be able to know for sure that the game is going to end with one of these two players winning. Okay, if the game is not destined to end in a draw. So if it's going to end in a draw, it will go on forever. So, and of course, all of this is under the assumption that both players are playing optimally. So what we get as a consequence of, this sequence of subsets increasing to this set is that when you look at the probabilities, they also increase to the, as n goes to infinity, they increase to the corresponding probability without level n. Okay, so as n goes to infinity, small nW1B superscript n, this increases to small nW1B. So in other words, we will focus on analyzing this and then take the limit to get an idea about what this is. Okay, so similar results will hold for the other classes of vertices. Okay. So before I go into how I set up certain recursions, I just need to introduce a few notations. So basically G sub B indicates the probability generating function corresponding to chi sub B. If you recall, chi sub B is the offspring distribution of a vertex conditioned on the vertex having color blue. Similarly, G sub R is the probability generating function corresponding to chi sub R. And then here are some special notations. Basically, these are notations I introduced to make my life simpler, where one of the coordinates in these two functions equals 1. Okay, so G sub B superscript 1 of X means that the first coordinate is equal to X, but the second coordinate is equal to 1. Okay, so all these come in handy when I am solving the recursions, basically. So these are just notations, and I can come back to show you these in case you want to see it further, like in case that you forget. So what I am really looking forward to explaining is how these recursions work out, and of course this this whole idea of self-similarity and independence that are incorporated in the Galton-Watson branching process play a vital role in us being able to set up these recursions. So for example, if you look at a vertex B and you ask for the event that that it belongs to capital NW1B superscript n plus 1. So what does this mean? This means that first of all, because it's in NW1B, this means that the color of the vertex V has to be blue. Okay. Now, if you start the game with V being the initial vertex and P1 playing the first round, then what does this definition tell you? It tells you that P1 wins the game because you have a W here, and she's able to win the game in strictly less than n plus 1 rounds because of this superscript. So that means that in the very first round, P1 has the luxury of choosing a child, let's say U of V, that has to be a blue child. Why? Because V is blue and P1 is only allowed to move the token along monochromatic edges. So this has to be a blue child of V, such that if you now look at the game that begins with U, then P2 is playing the first round and P2 loses in less than n rounds. I hope this is clear. So once again, P1, who plays the first round here, has the luxury, is able to move the token in the first round from V to a blue child of V, let's call it U. Blue because monochromatic is the only kind of edges she's allowed to move the token along. And U must be such that if a game begins at U with P2 playing the first round, then P2 loses the game in less than n rounds. Okay, less than n because here in the first round you have already ended up spending one round. So the remaining would be n. So you start with n plus 1 and then you go to n. So hopefully this recursion is clear. So now I'm just, all I'm doing is I'm just writing this mathematically. So what does this mean? This means that you will have to belong to this set, capital NL, 2, B superscript n. Okay, so this means that P2 playing the first round loses the game in less than n rounds. Okay, so what I have done here is I've simply, this is the probability that you have at least one child, U of V, which is in capital NL2B superscript n. This summing over that you see here, this M1 indicates the number of blue children of V, M2 indicates the number of red children of V. Why this sum starts from 1 is that if V does not have any blue child, then P1, who plays the first round, will lose the game. Okay, so that's why this must start from 1. And then when you simplify this, again, this is chi sub B because you have conditioned on V having color blue, so its offspring distribution is chi sub B. So hopefully this, this is clear about how I get this expression. And then when you simplify this, you get this expression where this G sub B superscript 1 is precisely what I have here. Okay, that's why these notations are useful. Likewise, you can find what NW1R superscript n plus 1 is going to be. Okay, so all that will change is that this blue here and this blue here will change to R. Okay, and also this one here will change to R. Okay, so this is how we go about.
One question, Moumanti,
yes,
in doing this recursion, I'm slightly confused. Do the players get to see the entire tree at first and then they start moving, or are they seeing only the next generation?
No. They see the entire tree. This is like a full information game. They know the entire tree. Otherwise, you cannot use this sort of strategy, I'm pretty sure.
Yeah, but, okay.
If the tree is sort of unfolding in front of you, I seriously believe that it would be a very different analysis. Like,
okay.
This whole quenched versus annealed kind of thing will probably take place, I think. But I'm not even there. Like, that seems like a very difficult question. The other side of the recursion is when you want to find the probability of a vertex V belonging to one of the losing sets. Okay, so NL1B superscript n plus 1. So here it means that if P1 plays the first round, then P1 loses the game and she ends up losing it in less than n plus 1 rounds. Okay, so once again, because you have a B here, the vertex V has to be of color blue. Okay, so one possibility is that the vertex V has no child that is of color blue, in which case P1 immediately fails to move the token in the first round and therefore loses the game. The other possibility is the following, that V does have blue children, but none of them is favorable towards P1, meaning P1 is forced to move the token to a blue child of V, such that, let's call this blue child again U, such that when you look at the game that begins with you and P2 playing the first round, this game is won by P2 and she can win it in less than n rounds. In other words, every blue child U of V has to be in the class NW2B superscript n. So you see the slight difference in the analysis here. It's just that you need one such blue child from which, such that if P1 moves the token to this blue child, she's guaranteed to win. Here, there is a compulsion for P1 that every blue child of V is in capital NW2B superscript n, so that no matter where P1 moves the token, she's doomed to lose the game. Okay, so here it's a slightly different computation. So this part is simply the probability that the V has no blue child, and this part is the probability where V has at least one blue child, but every one of them belongs to this capital NW2B superscript n. So that's why you get this expression. And then when you simplify this, you get this. Once again, I'm making use of the notation that I showed you a couple of slides back. Likewise, you can find what NL1R superscript n plus 1 is going to be. So you can also repeat these recursions when you want to find probability of like small nW2B superscript n plus 1 or small nW or small nL2B superscript n plus 1. You can similarly apply these. You just have to keep in mind that here we were talking about monochromatic edges. There you have to talk about non-monochromatic edges for the first round of the game. Okay. So I just want to quickly show what these recursions lead to. Of course, you know, it's a horrid looking expression, and the general expression is even more horrid. Here I'm just looking at a couple of colors. So you get a recursion of this form. So it's, as you can see, it's a, what do you call this, a 4-step recursion. So you're looking at NW1B superscript n plus 4, and that gets related to NW1B superscript n via a function of this form. So the actual form of the function is not so important. What we can say is that NW1B, so when you take the limit as n goes to infinity, keeping in mind that capital H1 is going to be a continuous function, you can say that NW1B will be a fixed point of capital H1. Moreover, what we can say is that because capital H1 will actually turn out to be a monotonically increasing function, so you can say that NW1B will be the minimum fixed point of H1 in the interval 0, 1. Okay, likewise, this is a result for NW2B. So NW2B will be a fixed point of this function H2. When you take into account the fact that H2 is monotonically increasing, you can conclude that it's actually going to be the minimum fixed point of H2 in 0, 1. Okay, so this is my last slide. Hopefully, I'm not going over time. This is just a glimpse into some other kinds of results I looked at. So some special trees that I studied. So my paper also has some inequalities, but I felt like this is a more interesting phenomenon that I wanted to show you guys. So, and it has a sharp contrast with the kind of results that Holroyd and Martin ended up having in their paper. So we look at a bi-type binary Galton-Watson tree. What does that mean? So first of all, binary Galton-Watson tree, at least when it comes to me, the definition is that every vertex will have either no child or exactly 2 children. So because this is a bi-type binary Galton-Watson tree, so again, there are 2 colors involved, blue and red. So given that V is a vertex whose color is blue, it has probability P0 of being childless. PBB, which indicates the probability that it has 2 blue children, PRR indicates its probability of having 2 red children, and PBR indicates its probability of having 1 blue and 1 red child. Okay, likewise, you define the offspring distribution for when the vertex is red. So I briefly mentioned the set capital ND1B, ND2B. Those are the sets of vertices such that if you start the game from such a vertex, and if you let player PI, so I is either 1 or 2, player PI play the first round of the game, then the game ends in a draw. Okay, so that's the D stands for draw. And so small ndIB is the probability that, so conditioned on the parent vertex, or sorry, conditioned on the initial vertex, let's say it's the root being blue, that if PI plays the first round, then the game ends in a draw. Okay, so likewise, you define NDIR. So R indicating that the root is red. So when you look at these probabilities for this setup, okay, for the bi-type binary Galton-Watson tree, you see something quite striking happening. It's very like almost like a 0-1 law, unlike what they found in case of binary Galton-Watson trees, no bi-type. So they were studying just binary Galton-Watson trees, and they had like a phase transition happening for the draw probabilities. For me, what I find is that the only case where you have draw probabilities positive is where P sub BR, which is the probability of a blue vertex having 1 blue and 1 red child, and Q sub BR, which is the probability of a red vertex having 1 blue and 1 red child, both of them are equal to 1. Meaning you get this, very like this tree where, let's say the root is blue, then you have 1 red, 1 blue child. Each of them has 1 red, 1 blue child, and you continue like that. So, and in that case, obviously the draw probability will be equal to 1, no matter who starts the game, because always every player has room to move the token. Okay, so the game never comes to an end. In all other cases, so which is kind of the extreme thing, in all other cases, when P sub BR and Q sub BR are not both equal to 1, you find that the draw probabilities are actually 0. So the games are almost surely going to end in finite time. So, and similar conclusions will hold if you consider the draw probabilities in the misére game, or if you consider the win probabilities for escape or in the escape games. Okay, so this is something that I find quite striking. Yeah, so this is the end of my slide. And so, yeah, thank you so much.
Thank you, Moumanti. So any questions, comments?
Just one question.
Yeah.
You see, are there any, the mean matrix of this multi-type process, right? You are looking at the 2-type Galton-Watson process, right? Essentially.
Yes.
The mean matrix plays a role in determining about the
right. Yes. Sure.
Now,
sure. The eigenvalue, the largest eigenvalue. Yeah.
Right. Are there any other characteristics of that matrix that play a role in the present analysis?
I did try to see that, but I couldn't pinpoint anything like because that is something that Holroyd and Martin focus on in their paper, like comparing, the threshold for the tree to become infinite with positive probability and the threshold for where the drop of probability becomes positive. They try to compare these two things, and I tried to do the same. So here, of course, you can see this is like a very extreme thing, but I also tried to analyze bi-type Poisson Galton-Watson tree, and I could only do very pretty elementary analysis. So I really couldn't connect the two things, to be honest. So yeah, I don't know if that exists.
I see.
Yeah.
I thought somehow there is this stochastic comparison of random variables, right? X is stochastically larger than Y and so on. In the same way, if there is some kind of a stochastic comparison of the number of blue children, number of red children, and so on, I thought that might play a role. Okay. Thank you.
Yeah, I mean, this is something I feel like there is like such a treasure trove of questions in this area, like that people can just plunge in and try to think. I really need to read up more about like multi-type Galton-Watson trees to think further on this. But thank you so much for that suggestion. Yeah.
Thank you.
Other questions?
Yeah, I was wondering if for some special values, I mean, so special distributions like geometric or something, could you say, would you also have like an explicit formula and for where the phase transition occurs?
Like I said, for the Poisson one, I didn't have an explicit formula. What I had were like all these conditions for which, okay, the draw probability will be something, I forget now the results, but as lambda grows or something like that. But it wasn't explicit. I mean, I wasn't super happy with the result myself, but I didn't try geometric, to be honest. So
okay.
Yeah.
But I also wanted, I mean, so this lemma that you have here is also a phase transition of sorts, right? It's just saying
it
that
is, but it's just so, so kind of jarring. It's like a very
Yeah.
extreme thing. So
Right,
yeah,
right.
yeah.
Okay, thanks.
So what is the kind of result that they have? I mean, I didn't quite catch it.
Oh,
Holroyd Martin.
their result is something like, so let's say that P is the probability of a vertex having 2 children. So 1 minus P is the probability of it having no child at all for the binary Galton-Watson tree. And then they show that like with P increasing, there is a threshold, let's say P sub C, beyond which, the draw probabilities become strictly positive. And I forget if they talk about, so they do talk about continuous versus not continuous phase transition, but I forget the exact result.
Mm-hmm.
Yeah.
So also, oh, sorry, there was, I had let me continue. I mean, there's a very basic question of games which I don't understand, maybe very naive. So when this is under the assumption that each player is playing best to win, right?
Yeah. Trying their best, yes.
To win or to not lose. Are they the same thing or not?
So, okay. How would I answer? I think that I would say that they're trying their best to win, not just not lose. That would be sort of my answer. But yeah, now that you asked that question, like I also feel a little confused how to philosophically answer or not philosophically answer the question.
Okay. But
Yeah.
I interrupted some other question someone was asking. Maybe we can go to that.
Oh yeah, sure.
Yes, there was another question, maybe. Okay, so maybe not. Okay, if not, so are there any other questions? Okay, if not, so Moumanti, thank you for this very nice lecture.
Thank you so much for the opportunity.
No, it's great. Okay, so now there is a break. For those who are at IISc, there is a coffee and tea arranged upstairs. I guess we meet back at 3:30, I guess.